Okay, so thanks for calling into today's Permafrost Collaboration Team monthly webinar series for the month of November. So Meredith mentioned we're going to do an hour and a half today. I think this is in part because Koli's on the phone and he tends to talk for a long time. So I wanted to give him his time and space. So we'll have 3 presentations today, along with some IARPIC collaborations member updates. So we'll start with 2 presentations discussing some long-term field observations on permafrost and active layer dynamics that I guess that have been going on for probably like 2 to 3 to 4 decades or so across the Circumarctic. Both of these activities are part of the global Terrestrial Network for Permafrost, the GTN-P. So we're going to be hearing from Dr. Dmitry Streletsky, otherwise known as Dima. He's chair of the GTNP, and he'll provide an overview of the past, present, and future activities of the Long-Term Observation Network. And then Dr. Nikolai Shiklemanov for Koli, PI of the CALM program, will provide an overview of the Circumpolar Active Layer Monitoring Program, which is the GTNP component that deals with the active layer. So just to give you a little background info on the dynamic duo, Dima and Koli. They're both professors in the geography department at George Washington University in DC. They both received PhDs in climatology from University of Delaware. That focus in their research largely focuses on climate change impacts on permafrost and infrastructure across the Circumarctic. They both lead and participate in several NSF-funded projects. They have more than 50 publications in peer-reviewed scientific journals. They teach several undergrad and graduate courses at George Washington. And pretty much whenever I email them in the summer, I get an out-of-office response. I think they're basically field junkies across like North American Arctic and also the Eurasian Arctic during most of the summer. Yeah, and their research primarily focuses on documenting evidence of rapidly changing climate conditions on natural ecosystems, infrastructure, and society. So Dima's going to kick it off today with the overview of the GTNP, and then Koli's going to follow on by talking about the CALM program. And then after Dima and Koli's presentations, Michelle Mack from Northern Arizona University will provide an update on the International Arctic Science Committee, or IASC, Terrestrial Working Group. Okay, all yours, Dima.
Cool, thank you, Ben, and thanks for having us today. I think it's perfect timing. We just released a new strategy and implementation plan yesterday, and that document I'll show in a presentation basically outlines the major developments of the network that some of them I'm going to cover today. So today I will just briefly mention a few things about the recent network activities, sort of related a little bit, put it in a perspective of overall observations, and discuss a little bit in detail what happened within the network over, let's say, last several years, okay, and show you the database, which I think is very great resource of data on permafrost temperature and active layer thickness. So basic idea behind GTNP, right, that it's a primary international program that is concerned with long-term monitoring of permafrost in both Arctic, Antarctic, and high altitude environments. It was very much reorganized by Global Climate Observing System of United Nations as one of the efforts to monitor one of those 50+ essential climatic variables. So the main purpose of the network is to operate a sustained, comprehensive long-term monitoring network in order to provide consistent, representative, and high-quality standardized long-term data series of selected permafrost parameters such as permafrost temperature and active layer thickness at key sites, and assess their state and change over time. And here you can see the example of a maps which we just downloaded from IARPIC, right? So on the left you see permafrost temperature distribution, and on the right you see active layer thickness over most recent data, which was recently published State of the Climate report, and that's one of the deliverables of GTNP, providing data for such assessments as an Arctic report card, State of the Climate, and various national and international assessment reports. Now, a little bit of a history. Interestingly enough, that we have more than a century and a half of ideas about this organized sort of monitoring campaigns tailored at determining changes in various environmental components, coming back to the first International Polar Year. Karl Weiprecht, he was Austro-Hungarian captain, was largely behind international attempts to sort of bring together various countries in order to study environmental change and their causes. And interestingly enough, during the first IPY, actually, permafrost, or we can say the upper permafrost, or the soil temperature, was monitored at 14 stations, and some of those stations located in the northern hemisphere, some in southern. You can see a map shown here. And interestingly enough, 4 of those locations, at least in the Arctic, monitored permafrost temperature over almost 2-year intervals, and with majority of this data never been analyzed. And I think this is very important lesson that we learned from that time, that despite large effort and undertaking of bringing various international components, if this data is not being stored and accessible, it basically undermines the entire effort of the monitoring. So keeping that in mind, we're moving very quickly to the GTNP, and GTNP was organized by the Terrestrial Observation Panel for Climate, TOPS, and implemented by the International Permafrost Association in beginning of 90s under the Global Terrestrial Observance System. You see quite a few here, right? There are various networks on hydrology, glaciers, and permafrost, and it all feeds to a Global Terrestrial Observing System of GCOS, which is global, right? Climate Observing System, which was designed in support of United Nations framework on climate change. And there are 2 major components within GTNP network. One is focusing on active layer monitoring, and another one on thermal state of permafrost. So despite that this large effort was conducted, it was relatively disconnected in terms of participants, because there were different efforts in various countries in terms of monitoring. But really, the network was reformed in the beginning of 2010s under the Page 21 project. So this is a large EU project that was primarily managed by Alfred Wegener Institute in Germany. And mostly because of the large monetary investment from European Union, this network was reformed, and this reformation allowed to establish relatively effective, I would call it, governance structure. It allowed to create data sets which followed best international standards and practices for data and metadata. It allowed to establish pretty comprehensive data management system, which I will showcase in a few minutes, which basically allows searches, visualization, and output of permafrost data in common standards. And also it allowed to sort of reevaluate permafrost temperature and active layer thickness data in model-ready formats. It's not a secret that very few models feeding in previous IPCC had permafrost representation. it's not because permafrost physics wasn't understood, it's because there was a lot of problems with validation of data. Basically, permafrost community wasn't ready to provide one harmonized data set which could be easily integrated in one of those Earth system models. So the idea was to sort of harmonize all the data and provide it in some form that can be easily implemented within Earth system models. Now here's a slide showing current governance structure, and the idea that network is based on national correspondence, and recently we introduced young national correspondents. Those are people responsible for sort of in-ground collecting data from their corresponding countries. We currently have about 50 national correspondents in across 25 countries that manage data collection, and all this data are being provided to the GTN-P data management system, which is located currently in Arctic Portal in Iceland, okay? And this work is being overseen by Secretariat, which is located in Alfred Wegener Institute in Germany, and we have both steering committee and advisory board, which sort of communicate this information across various international and national networks. So what do we have right now? We have about 1,350 boreholes. You can see on the map, about 250 active layer sites. And here you see the location of those sites. Not all of them have data. Those are showing sites that have metadata only, right? So it's not necessarily that currently we have data on all of those boreholes or active layer sites. But what we're trying to do, we're trying to implement or ingest as many historical data as possible currently in the system, and we're trying to do it in collaboration with National Snow and Ice Data Center. But if we sort of look at the distribution of data, and I think it was major publication published in 2015 after launch of this database, we can see that some of the regions are relatively well represented by boreholes or active layer sites, right? Those are regions of, well, Alaska is doing relatively good, Mackenzie Valley, Western Siberia, but some regions, you know, have sites that kind of one site per several million of square kilometers, right? So basically that publication wasn't as much analyzing the data per se, but looking at distribution of sites and calling for further improvement of observational networks. And here I'm showing the web page and a database. So basically it's gtnp.org, okay? And this web page has information on national correspondence. It has a lot of infographics, and obviously it has a large portion that is database itself. This database has two major components, just like two major components of GTNP. It has permafrost temperatures and data on active layer thickness. I'm not a data scientist by any means. I'm not gonna go into detail into this diagram, which describes data management system. The only thing I know about it that this is state-of-the-art flagship product of Arctic Portal, and they're developing other sort of data sets that being sort of integrated using the same platform. This data management system allows searches, it allows download of data, it allows simple automated visualization, download of data in various common formats as well as NetCDF. If we look at sort of contributions of various countries in this very large international efforts, you kind of see that on top is a number of sites that borehole sites, right? Thermal state of permafrost. You see that United States is third one, right, after Russia, Canada. And on the bottom is number of active layer sites per country, right? And you see that actually currently United States has pretty much the leading role, okay? Since we are tracking mostly for North American, I think, audience, I want to showcase major data contributors within the United States. For active layer thickness, this is CALM project, right? Circumpolar Active Layer Monitoring Network, which Koli will talk in a few minutes. For thermal state of permafrost, this is corresponding network, right? TSP, which is hosted by UIF. And USGS obviously plays a very important role. So two major government agencies, USGS and RCS, right? Those are two major contributors of data, primarily on permafrost temperature, but also a little bit on active layer. And there are other smaller contributors that are not even within the United States, right? So even within state of Alaska and Antarctic contribution, you see that there are diversity of both private or NSF funded contributions as well as government. So just to show you a little bit of what you can do with this database, if you go and download this data, right, you obviously can calculate averages and visualize it. This is example of sort of recent snapshots of permafrost temperature since the last one, which was done during International Polar Year. So it was snapshot of 2008 and 2009, right? And you see basically permafrost distribution. This is ground temperature, permafrost temperature at a depth of 0 annual amplitude, okay? And as you expect, you see some bioclimatic gradients, right? Especially you can see it along the transect, sort of in Alaska, that moving sort of towards Arctic coast, right? From discontinuous to continuous permafrost temperature is decreasing, right? So this is something that we're all aware, but this is, for the first time, was done using this data management system, right? And you see some example of Antarctic, where you see much colder permafrost around the coast, and only Antarctic Peninsula has permafrost temperature, which is near 0 degrees C. So we can look at the trends, right? And again, I'm just talking about sort of network activities, but just to, you know, give you some signs. Those are the trends, and you can see those in latest State of the Climate report, right? So those are till 2016. And basically, by looking at those trends, you can see that permafrost temperature is increasing in most of the regions, well, with a little bit exception of Antarctic. It really close follows air temperature trends. And as you heard many times probably from many permafrost scientists, and this is very well seen in comparison of Northern Alaska versus Interior, the cold permafrost temperature is increasing at a faster rate than warm permafrost, that permafrost that's sort of near thawing, okay? So to conclude, just a few recent developments. We are very excited that we're finally able to publish that strategy and implementation plan that I was trying to attach, and I don't know if it attached to that presentation. That's when my computer crashed. But it's available for download through the Library of Arctic portal. And it basically covers in detail historical developments or of challenges that network is facing. We are relatively small number of people compared to other terrestrial network, but we're trying to collaborate with others. A recent collaboration with Global Crosshair Watch, for example, we're trying to develop best practices for permafrost monitoring to be implemented through WMO. We're trying to be more proactive for periodic data submission, because at this point we have national correspondents submitting data as, as the data comes. We're trying to standardize it to receive sort of annual calls for data. We are very excited that we just submitted application for its world data system, and hopefully we will be approved as a regular member. We're trying to publish the results in annual reports, such as State of the Climate. And I am not showing any new data or any new graphs, because as we speak, there is a publication being submitted to one of the high impact journals that is written by pretty much 50, I guess, national correspondents and members of GTN-P, which compares how permafrost temperature changed since last International Polar Year. So this is basically a comparison of most recent thermal state of permafrost relative to the one established during the IPY. And last but not least, we're trying to organize workshops at various conferences and sessions, and to involve young scientists. We're working closely with Apex and with Permafrost Young Research Network to try to involve next generation of scientists in global terrestrial network of permafrost. So thank you for this opportunity, and we have a Facebook page, we don't have a Twitter, and of course we have gtnp.org, where we post all the most recent data is available, tutorials on how to use data. There are various maps and visualizations that can be used for not just scientific, but also for public and outreach purposes. Thank you.
Yeah, nice. Great presentation, Dima. Thank you.
Yeah, I'm trying to leave more space for Koli. Well,
yeah, that's a good idea. I saw him sitting behind you, so maybe we'll.
Ben, can I just comment very short?
Yeah,
comment?
yeah. Maybe we can ask a couple questions real quick for Dima. Go ahead, Vladimir.
Okay, yeah, this is comment. Yeah, thank you for good presentation. But Dima, you have to, and I will send you the slide. Include in the history a very important meeting in Geneva in 2013. Actually, it was the first meeting of national correspondence. So that was very, very important meeting, and you have to include it in your history slides. Okay, I will send it to you.
Yeah, thank you, Vlad. And I have that slide, but I was deleting a lot of things. Yeah, you're right. I shouldn't delete that one. But
yeah, it was. Yeah, every 2 years we had meetings that time. So 11, 13, 15. Yeah.
Thank you for that.
Awesome. Thanks, Vladimir. Hey, Dima, that's a really, really nice presentation and a great effort. What do you think the long-term outlook for GTNP is? Is there a pretty solid funding going forward for the next several years?
Are you kidding?
Yeah, so you can look, and I think it really reflects in that strategy and implementation plan. I didn't talk at all about the challenges, but we were really struggling over the last couple of years to keep this effort going, because there was a lot of funding during a lot of monetary investment put into this network, during the page 21. And basically when the project was over, we were left with very complicated system that required a lot of funding. And we were facing the choice to kind of scale down or to try to keep it going. And last year was very challenging, but looks like for the next year we'll have at least few projects in Europe that have some funds directly or indirectly that can support various network activities. But also I would like to thank IASC, which support a lot of meetings and workshops in the past. So hopefully we have no funding, absolutely no funding for GTNP as a network, but we're trying to kind of survive on other related projects and keep it going.
Okay, cool. Thank you. Yeah, thanks, Dima. Okay, Koli, do you want to take over?
Sure, and I'm going to talk about one of those projects, right? So this is a CALM project, which is again, part of the GTN-P dealing with long-term monitoring of active layer and upper permafrost. All right, so again, the objectives are pretty straightforward. Dima pretty much outlined it. It's just basically develop and maintain program of long-term active layer observations. Again, this is just an integral part of the overall GTN-P effort, and obviously develop the database again, which we are kind of doing in very close collaborations with Dima. We have offices next to each other, and with GTN-P in general. A little bit on CALM history, I should mention that the CALM, the Circumpolar Active Layer Monitoring Program, was probably the first international program dealing with standardized permafrost-related observations, right? So again, it was visualized in late 1990s, right? So by Jerry Brown, obviously. And then the initial finding and initial assimilation of data sets from Russia and observations in Alaska started in the very early 1990s. First of all, as part of the ITEX program. Again, there was a CALM component attached to International Tundra Experiment Program, right? So, and then we were sort of continued to develop under the series of National Science Foundation projects, funded projects, started from CALM 1 through, we are currently at CALM 4. And obviously, periodically, we do have quite a few workshops, usually aligned with international permafrost conferences to coordinate our US activity and Russian activity with kind of a broader international community. All right, so just Dim already mentioned about the, the network, GTN-P network, and again, CALM is just a component of GTN-P, but here I kind of, show you the map of CALM network. So as of 2016, 2017, we have 115 active sites. So those are sites which continuously report annual active layer observations. Majority of those sites, for obvious reasons, are located in Arctic and subarctic lowlands. However, we do have in our database, we do have some sites in high mountain regions, for example, in Tibetan Plateau, right? So in, in China, but obviously those sites are not active as a CALM sites at this point, and I will explain why. As far as NSF CALM project is concerned, we have 82 active sites directly or indirectly supported by the NSF funding. 33 of those are located in the United States and Alaska, and 50 in Russian Federation. So at the beginning, when we were developing the CALM program, that was, again, I already mentioned it, that was the first international program which was collecting permafrost-related data. And essentially, we were trying to get, and at least rudimentary, analyze and archive everything we can get. And that was included direct active layer measurements by probing or by other means, as well as temperature data. But since the last polar year, right, so in around 2008, when the GTN-P was developing, we kind of decided to specialize more on the spatially oriented active layer measurements done by probing. And the reason for that is quite apparent, because active layer, being at the top of the permafrost, experience an extremely high spatial variability. So basically measured in one location doesn't make much sense, right? So because you can wander a few meters and can get completely different values. So the CALM right now is specializing on spatial observations. So basically all observations, all our sites consist of either grids, which range from 1 kilometer square, kilometer by kilometer grids, to smaller 100 by 100, 1 hectare plots, or the series of smaller transect or smaller 10 by 10 meter plots. The only reason to to be a calm site, the one important characteristics is that each of those measurements should be representative of generalized landscape conditions found within the area, right? So we get a more or less representative sample of what the active layer thickness for any particular landscape is. And obviously it is impossible to do with just a point location. Another problem which we kind of try to address at the beginning is when do you measure the active layer thickness? So obviously active layer thickness, that's a maximum soil depth, right? So by definition. And those things vary from year to year depending on climatic variability and possibly change. So we have decided long time ago, like 20 years ago, so then rather than trying to get the active layer thickness per se, we will try to get the soil depths at particular date. Obviously, for logistical reasons, it's extremely hard to do, to be at each of those sites in particular, in particular date, right? So, but at least we are trying to do it within the same kind of a 7-day period, within the same week. So essentially, even though we are calling it the active layer because we are trying to get it at the end of the sowing season, technically this is the end of season soil depths, right? So, and that's kind of what needs to be understood. And the reason for us to do it is so we can compare the long-term trends. All right, so, and what are the results of all those observations? I mean, this is the graphs which comes from the latest Arctic report card, which is about to be released at AGU, as far as I understand, which shows you anomaly for different inactive layer thickness for different sort of a representative regions, covered by calm observational program, right? So we have Alaska North Slope, approximately 20 sites here, and West Siberia, East Siberia, Greenland, Russian European North, and Russian Far East, right? So number of sites here, obviously it's not the sites, all the sites which have reported data in 2016 or 2017, but only the sites which have at least 20 years of continuous record. And and obviously to be, everything was scaled down and presented as anomalies so we can compare trends. And I'm not going to talk much about each of those regions, maybe with exception of Alaska. But we can see that, West Siberia shows a pretty significant increases in active layer thickness, so is Russian European North. And in fact, in Russian European North, so this is the Russian Arctic west of Urals, we have already lost one site out of 4 we used to have, simply because the active layer progressed to the depths kind of below 2.5 meters, which for any practical reasons kind of doesn't make much sense to continue observation. So the site has degraded completely, and we are on the verge to lose another site there. So there we are experiencing pretty significant increases in soil depths. All right, so now let me kind of talk a little bit about Alaska. Obviously, that's where, since we are funded by NSF, that's where majority of our effort goes. So if you look at the calm observations in Alaska, again, just considering kind of a spatial grids, we have 25 of those things on the North Slope, 13 in the interior, and 2 in the Seward Peninsula. And good deal of those sites, as you can see on that graph, have 20 years or more record, right? So on the North Slope, with exception of 223 sites, have really long-term active layer records. In interior, well, we have only 4. In Seward Peninsula, we have just 2 sites, but they have 18 years of record, right? So each. On top of that, we can see that there are those small dots kind of represented here, and they are 16 USGS North Slope sites, where back in the day, active layer was inferred from the temperature record and submitted to our database. And the record there ranged from 2 to 12 years. But again, since the inception of TSP and GTNP, all that data is now not going into column, but rather archived as temperature records in the TSP and GTNP database. So if you look at the trends for Alaska, we can see that that's kind of not very not very significant for the nose slope, and we'll look at that in details in a couple of slides. And the only sort of red dots we can see are in Alaska interior. So there we have 4 active layer sites, and here these are kind of 20 years or more of record, and here we see a pretty significant increases in the active layer thickness, right? So on top, we can see degree days of sowing, and for consistency, they are calculated for that particular region from the beginning of sowing till October 1st, right? So we are not kind of looking at all those kind of weird fluctuations after October 1st. And here are the active layer, active layer trends, and those are 2 sites representing the Fairbanks region, right? So in here we have a very pronounced trend, 1.1 centimeters per year. And this is the north, this is actually Vlad's site, Old Man, right? So not far from Coldfoot, right? So, and it shows kind of also a pretty serious increase, but obviously way behind the, the Fairbanks. Another example from Fairbanks comes from the Bonanza Creek LTR site, where we have a very long record, and we can see that up until 2010, it was pretty much on par. Obviously, the scales are different here, on par with Fairbanks kind of other Fairbanks sites, and then the site got burned, and we have kind of pretty drastic changes in active layer thickness. So again, at this site, we can really see the difference between burned and unburned sites. Obviously, the burned one experiencing much steeper trend, almost 20 centimeters, and almost 20 centimeters per year. If you look at the nose slope, on the nose slope, we have probably the most comprehensive active layer monitoring system developed. I mean, first of all, a good deal of our sites coincide or located in very close proximity to existing TSP sites and permafrost observational sites conducted by different agencies and university projects. But also our sampling strategy on the nose slope was deliberately designed to reflect that sort of a landscape variability. Again, so all sites are arranged along 2 latitudinal transects. One, the western transect, from Barrow down to Ivitock, and then we have 3 long-term monitoring sites here: Barrow, Etkasock, and Ivitock, which have 20 years or more of active layer records. And then we have a lot of sites arranged along the Dalton Highway. Again, the sites were selected to represent different bioclimatic subzones, different physiographic provinces, and different vegetation and landscape units within each subzone and physiographic province. So what we can get from it? Well, so obviously, since everything is tied pretty closely to landscape information, we can probably derive some statistics on the reaction of active layer to climatic forcings for different landscape units, and that's what kind of the example of that type of analysis and shown here, demonstrating that sort of the slope of those curves are slightly different for different landscapes located within the very close proximity one to each other. Obviously, this is not a big surprise, but at least with the 20 plus years of observations, we can assign some sort of a numerical values to those parameters. If you look at the long-term active layer trends, this is the western nose slope transect. Again, Barrow, Atka, Sock, Ivy Talk, we can see a pretty, relatively slight increase. And usually the foothills, which is Ivy Talk, kind of shows the trend similar to Barrow, while the Atka Sock is actually increasing quite dramatically, almost half a centimeter, quite a centimeter per year. Again, that's probably relates here. You see the degree days of thawing. Again, now that's from the beginning of thawing season till September 1st, because obviously we are talking about no slope active layer beginning to freeze at the end of August. And again, we can see that trends for sort of a central coastal plain and northern coastal plain are rather similar. However, the reaction of active layer system to that trend is much more dramatic in areas around Atka. So if you look at the eastern no slope transect, again, we can probably see some regional trends. The northern sides usually showing us, slightly smaller increases in active layer thickness over the 20-25 some years than the sites located, further south. So the other observations we are conducting at calm sites in Alaska and elsewhere, and this is the air and ground surface temperature monitoring. And the difference from your typical ground temperature installation is that, again, we are trying to address a spatial variability in the surface temperature, again, as it relates to the changes in active layer thickness. So usually within each of our, or majority of the calm sites, we have up to 9 to 10 thermistors installed, in different microtopographic conditions within each sites, right? So right under the vegetation. And obviously we usually have one mass to measure air temperature. And I don't want to talk much about those results because we are still analyzing it, and Anna Claney is responsible for this work, who is a co-PI on the CALM project. But what we can see is quite interesting. Here we can see the air temperature and ground surface temperature trends for one of the sites. I picked it as the most dramatic site, and that's located not far from Tulik Lake. And this is the mean monthly temperature for July. And we can see that the July air temperature gradually increasing, while the July ground surface temperature right underneath the vegetation is slightly decreasing. And if you look at the difference between the ground temperature and the air temperature for all of our sites, we can see the pretty dramatic increases across the whole, all bioclimatic zones and across all different vegetation types, but more dramatic on the Arctic foothills, where vegetation is obviously more pronounced. And here what Anna did, she just overlaid with a satellite-derived NDVI for those specific sites. Again, this is a very preliminary work, and we can see that NDVI is increasing, and our difference between the temperature at the surface for July, again, and the air temperature is pretty much increasing within the same, or at least similar rate. So basically all that's feedback to permafrost system attributed to vegetation, it looks like now with the 20-some years of continuous observation, we can probably see it and quantify. Now we are working on kind of, working out the details of analyzing this data. This is a very preliminary result. And obviously the other component of CALM, which we are doing in Russia and in Alaska, is the vertical position of the ground surface. So obviously the idea is pretty straightforward. When the ground thaws, that sort of ice segregated at the bottom of the active layer, that transient layer, can melt and result in pretty substantial subsidence. To monitor that subsidence, again, spatially, we are implementing two types of observations. One, in Alaska, we are using differential global positioning system, which gives us a pretty good accuracy on a vertical position. Again, we are getting how many? 36 measurements within each 100 plots. And in Russian sites, obviously, GPS technology is kind of harder to implement. We are using the very simple optical leveling. And we are conducting in Russia. There is actually one site missing. We are doing it in Chukotka as well, and few Alaskan sites. And here's an example of those type of observations. This is from recent Dima's papers about Borehole, where you can see the ground subsidence at different sites from 2003, and this graph comes from publication, goes to 2015. And we can see that it's not just the active layer thickness, which is increasing slightly, but the ground is also subsiding quite a bit. And it's not the monotonic subsidence, but we can see that probably the largest subsidence is attributable to the warmest summers, right? So which obviously not as surprising. And sometimes active layer freezes back, but usually it stays at that completely new level. And the other thing, again, what we are finding, that if you try to correlate the summer temperatures or degree days of thawing to the active layer thickness, just to the active layer thickness, and degree days of thawing and active layer thickness plus the subsidence, in a later case, we are seeing a quite a better result. So our R squared getting improved by sort of 10. And that's shown across the different landscapes. Here I'm just showing, only showing the Borehole example. And finally, again, we are doing a lot of education and outreach. Obviously, the column observations are exceedingly labor intensive. We have lots of sites, very short window of opportunity, because we got to get to those sites within specific time frame to provide continuity for our observations. And obviously we have a lot of each sites, if those are kilometer by kilometer sites, a lot of working and measurements to be conducted. So we are employing a lot of undergrads in our research just to put boots on the ground, but also providing them with a research opportunity to analyze the data and do something with it and to present it. And another interesting thing, especially in remote areas of Russian Arctic, we are now consistently employing representatives from predominantly indigenous community to perform at least some kind of a very basic observations for us on continuous basis. We are also collaborating with Yukon Tribal Council, right? So to do the same type of research in Alaska. And obviously Dima and I, kind of every summer, we are contributing to field permafrost courses, kind of again conducted in Russia. Next year it will be in Alaska. And another sort of our interesting outreach activity is related to research related to Inupiat ice cellars, predominantly in the in Borehole area, right? So again, so those are big ice cellars where people store the whale meat, and there were lots of reports of those things being collapsing, right? So and in 2006 we instrumented few of those cellars. And now we are watching closely what's happening to the temperature, but also we were working closely with the community to provide the map of those ice cellars, right? So because prior to that, they pretty much, the community didn't know where those things are. So we are continuing that type of work, and the paper was published by Kelsen Island a long time ago. I should have included the reference, and I think this is my time to finish. And again, sort of I provided an acknowledgement at the beginning, but here it is again. And obviously the 25 years of calm was funded by different NSF projects, but we also need to acknowledge logistic providers, right? So CHTM Hill, Polar Services, as well as our logistic providers in Russia, and the numerous students and researchers who have participated in collecting this information. So thank you very much.
Hey, great. Thank you, Koli. Thank you, Koli. Yeah, just to like kind of give a shout out to some of these long-term monitoring efforts and programs, and bringing in undergrads to help out with some of these field-intensive surveys. That was my first trip to Alaska was June 2001.
Yeah, you were part of the call, as far as I remember.
Exactly. Yeah, I was like an REU undergrad student with NSF, and Koli and Ken Hinkle and Fritz kind of drug me around the North Slope. So anyway, it's a very, very awesome program. I'm glad to see that it's continuing on for another, what'd you say, Koli, at least another few years of funding?
Well, we are working on the proposal, which we are hoping to submit, relatively soon.
Okay,
for the
great.
next round of call, yeah.
Cool.
And we're working on sort of lining up support from Russia, including financial support, to continue that type of work.
Okay, awesome. Awesome. Anybody on the phone have any questions for Koli and/or Dima?
Yeah, I do. This is Cristina. Thank you. That was really great. I'm not sure if this is a dumb question or not. Can you hear me?
Yes, yes.
Yeah. How do boreholes account for the fact that they are a structure that's put into permafrost? Do they actually also warm permafrost to some extent because it's a structure that's put into the ground? Is that accounted for somehow?
I can answer this question if you would like.
Yes, can answer that.
Okay.
Yeah. Well, it depends what kind of disturbances you are making when you install. So if it's deep borehole, of course we try to drill during the winter and make minimum disturbances, and usually it work done pretty good. So you don't see too much of the difference between area around the hole, even if it's like 80 meters hole, and surrounding area. But of course, the pipe itself and the casing, in many cases, they have some impact on upper upper soil temperature regime, and this may propagate maybe down to 1 meter for this deep boreholes with big casing. But deeper than that, it's pretty much there is no impact. Now, for what Koli was saying, they use pretty light equipment to install, and if they do any drilling, it's really very shallow drilling, there is practically no impact on the surface conditions. In this case, there is not much impact at all on temperature regime. If there's even a shallow borehole, there is some rod, like 1 meter. So again, upper part, maybe 20 centimeters, maybe 10, could be impacted. That's why if you measure surface temperature, it's always separate thermistor, so not included in the rod. So anyway, so there is some impact for sure, and answer is pretty much the lighter equipment and shallower installation have much less impact on the temperature regime. And if it's done properly and carefully, well, we can pretty much ignore the impact of the installation on temperature regime.
Okay, cool. And if we do observe an impact, does it diminish over time a little bit or not really?
Well, again, if there was no disturbances, then it will be pretty much the same impact. If it was, it will start to develop some, well, sometimes even just going to the site, just tramping around may change the conditions around it. In this case, of course, you may have some longer term impact. But again, because it's logger, so you visit it only once a year, and being careful walking around, it will not produce pretty much. In 98% cases will not produce any significant disturbance.
Okay, great, thank you.
Oh, any more questions on the phone?
Yeah, this is Michelle Mack. I have a question that's sort of related to Christina's. Just thinking of long-term vegetation monitoring plots, 20 or 30 years of monitoring, trails develop that compact the organic layer, and we see changes in drainage and big changes in species composition in those trails. I wonder if in the calm grids, do you see any of that compaction and shifts in vegetation associated with the grid layout?
No, we don't. I mean, our grids, first of all, our grids are pretty large. I mean, in Alaska especially, if it's kilometer by kilometer and 100 meters between stakes, so it's kind of highly unlikely that you will work the same path kind of, every year, right? So we are trying to do everything as uninvasive as possible. Yeah, plus it's once a year. For the smaller grids, we are actually not doing that sort of that standardized grid design. So we are, our sampling strategy is such that we are kind of trying to get, again, we can talk a lot about the sampling strategies, and kind of back in the day when we were working on it, we have one master thesis, and actually the couple of papers related to that, but we were really working on sampling strategy from the beginning to be as kind of less invasive as possible, but provide the representative sample.
Oh, that's cool. Okay. So then what you just said made me wonder a bit about with the grid layout. It seems like you could, well, maybe you're,
well, I mean, it's
too large,
again,
but looking at spatial contagion in permafrost, are you able to look at the scale at which there's covariance among points, or are most of your grid points too far apart to show much?
Well, no, we were doing lots of that work. We should probably repeat it. I mean, we've been doing and publishing a lot of that work around 2003, 2005. So basically when we get the first kind of 5 years and we look at spatial dependencies and lots of different things and levels of and scales of variability for different landscape units in different physiographic provinces and things like that. But the point here is that the calm grids, a typical calm grid is kilometer by kilometer, right? So, and we are measuring, and we are not like, sticking our probes at the same point, right? So again, it's within that sort of a general area. And the total sampling of the grid is 121 point. And usually it's wander off maybe by half a meter or a meter, or, sometimes maybe, well, I don't think it's, as much as 2 meters. I mean, from the sampling point, but it's not always the same location. And but what we are trying to get is that representativeness of the overall landscape. And we think that kilometer by kilometer and 121 points will give us that. So, and again, in each of those dots in each of my plot, there's lots and lots of points kind of going into that. Well, for every year. And again, so it's not like those vegetation sort of sampling plots in Tulik where I keep going to the same location day in and day out, right? So we are trying to get statistics.
No, I mean, we have
that's why they have boardwalks after all. I'm not criticizing.
Yeah, no, but I definitely have plots that I've monitored once a year where there's subsidence, but I'm always walking in the same place. I think that's the big difference.
Yeah, so that's the difference. We are trying, but your point is extremely valid, because in some places, and I don't think, I mean, it's really, we are watching it closely, and I don't think there is a concern for Alaskan sites, because there were lots and lots of kind of a thought put into how to develop that statistically representative but less invasive kind of a sampling strategy long-term strategy. But for some of our Eurasian sites, yes, there is a little bit of a concern, and we are now thinking maybe just kind of moving the sites within the the same landscape unit, but slightly kind of away from where 20 years of measurements were conducted.
Kola, I can add on 100 by 100 meter sites. It seems like it's smaller than kilometer by kilometer, but there should be no worry about it, because what we do, we actually mark only the two sites, and we walk from one site to another, just looking at this orienteer. So we're definitely not going exactly the same path, because there is nothing, no grid points inside of this 100 by 100 meters grid.
Yeah.
So, and in this case, once a year walk through this grid, I would guess there is some caribou migrating, passing this thing much more time than we do. So I don't think it will make it.
Yeah, that's what I meant by kind of by trying to develop that sampling strategy. Yes, I mean, and we have 100 plots. We kind of doing the same type of work. So the bigger disturbance we experience is obviously kind of a heavy equipment. And even in winter, when they draw for test drilling and stuff, oil and gas, and when they drive through the sites. But
yeah, that's right.
Okay, cool, great, great discussion, guys. I guess we'll.
Can I just one comment?
One more question.
One comment. So Koli, this July temperature. I would just suggest to be careful and emphasize all the time that it's July temperature. Yeah?
Yes, it is. I mean,
because especially biologists, they don't think about the difference, and they can say,
that's why I guess it was.
and they will say, why your temperature shows that the decrease in soil surface temperature, and borehole next to it showing still increase in permafrost temperature.
No, that's just kind of,
so be careful with that.
No, and I guess I try to emphasize that this July temperature.
Yeah, the trick is with increased vegetation, you also increase accumulation of snow there, and actually winter temperatures, if you will continue to year round, they will be actually higher, and mean annual temperature will be maybe even increasing, not decreasing.
Yeah, but this kind of is with the surface temperature, we are, again, the Anna right now, those are very preliminary graphs, and Anna is now kind of with her students, kind of they are doing and really kind of doing very tedious work, trying to see the kind of the thermistor placements and kind of when equipment was changed, and just kind of do all those type of things. But we understand, but basically we are using July simply so we can compare it with NDVI, right? So when this is the maximum.
Yeah, no, it's all good. It's all good, and yeah, if it's increasing biomass, you should expect decrease temperature under vegetation. Of course, it should be like this. But what I'm saying that to keep this picture a little bit broader, you have to look at the winter conditions as well.
Sure, no, but for us, I mean, the winter conditions, I mean, I didn't mention it, we installed cameras trying to get kind of the snow variability, but the winter temperature, I mean, we have the record, but it's without snow thickness. I mean, because vegetation has a pretty minor effect compared to snow when you kind of look at surface temperature versus air temperature differences, right? So, and we do not have a really good handle on snow cover yet, but we operate cameras and stakes which are trying to get at least some sort of a measure of how what snow is doing.
Okay.
So obviously the summer is a little bit easier to deal with because we know that this is vegetation which provide that temperature offset.